What kind of things would affect attraction between molecules? Well, we've done this before. It's called polarity. Remember polarity? What's the result of having a polar molecule? Well, not a charge per se. We call it a partial charge. All right, y'all remember how to predict whether a molecule is polar? Electronegativity difference. So if I have a water molecule which is made of an oxygen atom and 2 hydrogen atoms, okay, the oxygen atom is more electronegative, and so these electrons in the electron cloud around the hydrogen tend to be pulled toward the oxygen. Okay, so they're not out here very much. They're only out here a little bit, but they're around this oxygen a lot more because the oxygen's pulling on them. That makes this side of the molecule partially negative and this side of the molecule partially positive, because it's like the cover got pulled off these protons. Okay, the cover being the electron cloud, and it's being pulled off of it. Okay, you understand what I'm saying? So it's mostly just this one proton sitting over here in the center of this electron cloud for hydrogen. There's a partially positive charge over here. All right, if we drew the actual structure, we'd have a hydrogen and an oxygen and a hydrogen have a couple of lone pair electrons, and so we really have 2 partially negative centers and 2 partially positive centers over here. Okay, and that structure then creates polarity. Well, if I have another water molecule, well, that's positive, and this is negative over here. All right, partially negative. Okay, what part of this water molecule is going to be attracted to this molecule? The negative side is going to be attracted to the water molecule, or some part of it? The negative side is attracted to the positive side. Okay, so water molecules are attracted to each other based on where the positive and negative parts are. Okay?
They wouldn't stick together like that.
Oh, yes, they do.
I'm talking about like they wouldn't bond, would it?
Oh, yes, they do. Oh, yes, they do.
So I thought they were full.
They are, but there's still a partially positive and partially negative region within that electron cloud. Okay? And so they have a structure. In liquid water, about 2/3 of the water molecules are actually what are called hydrogen bonded to each other. And hydrogen bonding means that between this water molecule, the hydrogens are actually somewhere between covalently bonded and not being bonded at all between this hydrogen and the oxygen, another water molecule. Okay, it's not really quite just an attraction, not really quite just a covalent bond. It's somewhere in between. Okay, it's almost a covalent bond, but not quite. All right, and the result is we get this structure of water that where the molecules are in this arrangement like this, a highly structured arrangement. Actually, you can't really draw it two-dimensionally because it doesn't really work out very well. Okay, and that's why water, because of this arrangement, then water forms very clean crystals whenever it freezes, if you freeze it slowly enough. Okay, and in fact, the hydrogen bonding is very specific, not only as to direction, but as distance. Hydrogen bonded water molecules are further apart than water molecules that are not hydrogen bonded. Hydrogen bonded water molecules are further apart than water molecules that are not hydrogen bonded. Hydrogen bonded water molecules are further apart than water molecules that are not hydrogen bonded. So if you get all the hydrogen bonds to get working at the same time, you got ice. Ice is the result of getting all those hydrogen bonds locked up. Or you can think of it that way anyway.
You said hydrogen bonded molecules.
hydrogen bonded water molecules are further apart than water molecules that are not hydrogen bonded in liquid water. Well, even in solid water for that matter. Huh? When they're hydrogen bonded, they're not. I wouldn't want to say they like to be or don't like to be. They're just not as close together when they're hydrogen bonded. Because hydrogen bonding requires them to be a certain distance apart, and if you can rotate a water molecule around so it's not hydrogen bonded, you can actually get it closer together. Get the two molecules closer together than you can when they're hydrogen bonded. Okay? But water molecules are constantly moving, as are all molecules, as long as we don't have absolute zero.
Now, how would they not be hydrogen bonded as well?
Okay.
Water is H2O, and they would always be happy because they would always be polar and bonding polarity.
That's not hydrogen bonded.
Is that possible?
Yeah. But they don't like each other, so they're going to bounce off each other pretty quickly.
They would repel, right?
Yeah, sure. But they can get closer together that way. But once you kind of lock them up into the hydrogen bonding arrangement, there's a specific distance between this water molecule and the next one. Okay? But that sort of locks them together a little bit. But it's kind of like Velcro, too, in the sense that it locks up and lets go, and locks up and lets go. Does that make sense? As long as it's liquid water. When you freeze it, though, that locks up into it's locked. It's stuck. Okay? That's the nature of being frozen. All right? So polar molecules have more attraction than nonpolar molecules because they've got this strength of attraction between these partially positive and partially negative ends. Okay? There's an attraction between polar molecules that you don't have between nonpolar molecules. But even nonpolar molecules have attractions. Nonpolar molecules have attractions. If I have this nonpolar molecule and this one, and here's the nucleus on both, and remember, these have all the protons are down here in the center. So going around in the electron cloud are these electrons. All right? And the electrons are moving randomly. So not only do molecules move randomly, but electrons move randomly. Okay? So the electrons are moving randomly, theoretically speaking, or statistically speaking. If they're moving randomly, then some of the time, most of the time, there'll be an unbalanced electron density. Okay, density being the number of electrons in a given amount of space. So an uneven amount of density in electrons means that some of the time there's more electrons on one side than on the other. So this is a low electron density and a high electron density. See what I'm saying? Miranda, you with me? Okay. All right, so if I have a low electron density here and a high electron density here, what does that mean about the relative amount of charge on either side? Lower and higher and what? Okay. Well, it's not so much, well, it's kind of electronegativity, I guess. You said negativity. Which side of this molecule is more positive than the other?
The right side is...
This side is more positive than this side. But unlike a polar molecule, this is temporary because those electrons are constantly moving. So this electron density shift is going to happen just randomly. Okay, it's going to happen, but it's random. But if I have this molecule up next to this other one that has the same sort of electron density shift, now I've got a partially negative end over here and a partially positive end over here. What tends to happen? Well, they're going to be drawn to each other. They're not really going to bond. Bond really is referring to something a little bit different than that. It's a kind of bond, I suppose, but it's not what we would call in chemistry a bond. All right? But even this is really, really slight. Okay? But this is the basic idea This is the basic idea behind something called van der Waals forces. London forces. Okay, London forces. It's named for somebody. It's not the name for the city, by the way. It's very slight. But if I have a really large molecule, okay, I got these two really large molecules I've drawn out here. Okay, so I've got several different nuclei in here because I've got a molecule. Because of the way of the size and shape, there's more places for this electron density shift to occur. Okay? I could have an electron density shift here. And here. I might not have it here. It might be pretty even around this nuclei, or nucleus. Or here. Okay? But because I've got this shift going on here and here, there's a more partially positive end right here and a partially negative end over here. Okay? Well, that means I not only have just one place where I can have this shift, I can have two places where this shift is going on. Does that make sense to everybody?
And when you say shift, it just means like
it means that the electrons have moved around. Okay? Are you a football fan? Sort of? And a lot of times the offense in a football game, they'll get down in position, but then the backfield will move around before they snap the ball. That's a shift. Okay? Well, the electron's moving around, so you can have a shift there too. It keeps doing it. It's constantly happening. Okay? So I'm creating a situation where I've got partially positive and negative ends here and there. Okay? What purpose?
Yeah.
It's what happens. It doesn't have purpose. It's what does happen. Okay? Well, as long as I have this shift in electron density, there's the possibility of being attracted here and here. That's twice the amount of attraction than I had with the smaller molecules. Positive and negative. I'm sorry, I should be here. Okay? Positive and negative attracted, positive and negative attracted. Does that make sense? So the larger, the more elongated and the larger the molecule, the more likely you are to have those attractions. Does that make sense? Because you've got more places for the electron density shift to occur. Because there's more space there for it to happen in. Alright? So when we talk about the size and shape of particles making a difference in whether something's a solid, liquid, or gas, that's because there's more places for that temporary shift to occur. Okay? Alright, so let's say these particles are attracted together. But I'm going to move them around really fast. Okay? Anybody ever... I should have brought this little game in. I got this little game at home. I have my kids to play with in the carport, or the garage. And it's a tennis ball. And the target you throw it at has Velcro on it. Okay? So if you throw the tennis ball at the Velcro target, what happens? It sticks. Okay? At least if you have the looped end of the Velcro, okay, on the target. All right. But if I throw that tennis ball really hard, what do you think happens then? Yeah, it doesn't stick. It bounces right off of it, and that's what happens when you get these molecules moving really fast. If you get them moving fast enough, they don't stick anymore, because the force of the how hard they bounce against each other means they also have a larger amount of bounce energy. Okay? They bounce off each other harder. Okay? So, even though there may be a strength of attraction between particles, how fast those particles are moving can overcome that.